Hello, class, and welcome back to trigonometry. Last, we learned that there's two ways we can measure the angles. One is using degrees, and then we also discovered another way by measuring based on the length of the radius of a circle in a unit circle. That's 2 pi, so it's 2 pi for any radius. So now what we want to do is look at some applications here. Okay, so if we look at this figure here, we're going to set up a geometric relationship, and we've got some arbitrary arc length, S, and we're going to say that S relates to some other arc length that we'll call S1. And the ratio is maintained if we take the included angle in radians for S. So we're keeping S and theta on top. And then we're going to put the included angle for S1, theta 1, on bottom along with S1. So we've set up this geometric relationship. Now we're going to make life easy for ourselves, and we're going to let theta 1 be equal to so what's that mean? We let theta 1 equal 1, then that's 1 radian. Okay, because remember we're measuring our angles in radians now. Okay, so let's reset this here. We're letting theta 1 be 1, so that makes this very simple. And then over here, arc lengths. Now, what would the arc length S1 be if the included angle is 1 radian? Well, remember the radian is a radius, and if there's 1 radius in the arc length of theta 1, and of course that's going to be R. So now we're going to solve this for S, multiply both sides by R, and then divide that out, and we have it solved for S, and since that's a 1, any arc length can be calculated by taking the radius of the circle times the angle that the arc creates, the included angle. Okay, so that's what the remainder of the slide is telling us here. We're going to let theta 1 equal 1. Since theta 1 is a single radian, that means the arc length has to be R, the same as the radius, and that makes this this equation simple and allows us to solve for the arbitrary arc length that we didn't describe yet, and we know it's always going to be R times theta. Okay, so that gives us this theorem for arc length. S is equal to R theta. Okay, so now we want to apply this here, and we're going to find the length of the arc of a circle of radius 2, and the central angle that the arc creates is 1/4 of a radian, or 0.25 radian. Okay, so arc length equals R theta. So we just have to identify these parts. It has a radius of 2, so R equals 2, and then the central angle of that radius of that arc is equal to 0.25 radians. So S is equal to 0.25 times 2. Those are meters. Okay, so since the radius is given to us in meters, the length of the arc will be provided in meters, and that's going to be 0.5 meters. Okay. All right. Okay, now we're going to also talk about how do we convert. We've got two ways to describe our angle now. We can either use degrees, and we filled out an entire chart with degrees, and we can now also use radians. We've discussed how once around creates an angle of 2 pi in radians is equivalent to 360 degrees. So if we divide both sides by 2, we know that an angle whose radian measure is exactly pi corresponds to an angle whose degree measure is 180. So essentially we've whittled that down to 180 degrees is equal to pi radians. So if I find degrees somewhere and I want it in radians, I just give it as much pi as I need to make that many radians. I need 1 pi to make 180 radians. Okay, and the other way around here, if I solve this for radians, so I'm going to have 1 radian is equal to 180 over pi degrees. See, what we're doing here is just solving for 1 degree. So let's see how we can put that to use. Okay, let's put this idea to work here. We've got our goal of converting a degree measure into a radian measure. Now notice that some of these degrees were some of the interesting ones that we discussed when we filled out that circular 360 degree rotation all the way through. So it'll be interesting to see what those equivalent measures are in terms of radians. Okay, so let's do this. Okay, so let's remember first of all that 1 radian is worth pi over 180. I'm sorry, 1 degree is worth pi over 180 radians. Good time to point out that you can tell what type of angle we are talking about, degrees or radians, because if we put the degree in there, it's obviously degree. If we leave the degree off there, we must be talking about radians, okay? So, and a lot of times the radian measure will include pi, not always. We'll see that not always. But let's just remember that 1 degree is worth pi over 180 radians. And for part A here, they were asking for the radian measure for a 60-degree angle. So each one of these 60 is worth pi over 180. So we're just going to simply multiply the 60 times pi over 180. And for me, the best way to do that, you can reduce that in your head if you're, if you know, after you've done this for a little while, but I just want to show you something nice on the calculator. So if I'm working with this and I don't want to reduce it manually, I can take the fraction part, 60 over 180, and hit the math key, and I can ask for a fraction, and it'll automatically reduce that to its lowest terms. So that's just 1/3, 60 fits into 183 times. So in terms of radians, now don't forget, we still have the pi here. So it's 1 times the pi over 3. So of course we can just think of that as pi over 3 radians. So we now know that 60 degrees is worth pi over 3 radians. We'll do the same thing here with 150 degrees. Okay, to get the radians, we'll take each degree times what 1 degree is worth. And again, it's like 15 over 18, right? So it's 5 over 6. But we can go ahead and use that little feature. So we got 5 times pi over 6 radians matches 150 degrees. Okay. What if we have a negative angle? Well, all we have to do is put a negative sign in front. So negative 45 times pi above 180 negative pi over 4. Okay, so now we know 45 degrees, a very interesting measure in degrees, is pi over 4 in radians, positive or negative, depending on the situation. Now let's look at 90 degrees, another interesting measure. You might be able to see what's going on here, but we have our denominator of 180. Okay, so 90 is half of 180. So we're just going to write this as pi over 2. And that would be what we expect, since the entire circle, the 360 degrees, is equivalent to 2 pi. Let's do one more that's a little bit different from each of these. If I take 107 degrees, then I'm going to take 107 times pi over 180. What's going to happen is if you try and reduce this to lowest terms, it can't go any lower because it's an awkward ratio. So we're just going to go ahead and multiply it by pi. So if I take this 107 divided by 180, okay, so I've enforced parentheses here to make that one number, and I'm going to take it times pi. Then maybe it's better that we just represent this situation with 1.x. We'll use 3 places of accuracy, so we're going to bump that 7 up to an 8 because the next digit is 5 or better. So this would be equal to 1.868 radians. We know it's radians still because we didn't put a degree up here, okay? So that's going to take care of converting from degrees to radians. Okay, so we've just looked at converting degrees to radians. We use the fact that 1 degree equals pi over 180 radians. We're now going to look and go the other direction. And we're going to use the fact that 1 radian is equal to 180 over pi degrees. And we're going to take these radian measures and convert into degrees. So for part A here, we're going to have pi over 6 worth the radians, and 1 radian is worth this. So we're going to multiply it to get degrees, 180 over pi degrees. And the pi, if we're using pi in our radian measure, it nicely cancels out. So the pi cancels out and we get 30 degrees. Okay, and again, just remember that we know whether we're looking at radians or degrees based on whether it's got the degree symbol. No degree symbol, think radians. I mean, it's possible that there's a misprint or somebody forgot to put it there, and you might be able to figure that out from the context. But what we're generally looking for is whether or not there's a degree symbol. And then pi is kind of a giveaway for radians. So let's take 3 pi over 2 times 180 over pi degrees. Okay, and again, we know that the pi cancels out. And if you can see here, the 2 fits into 180 90 times. So we're going to take that 90 times 3, so 270 degrees. And of course, you can pump it into your calculator. So if I take the 3 over 2, take that fraction times the 180, and ask for lowest terms, we get the 270. All right, so let's look at C. Negative 7 pi over 4 times 180 over pi degrees. Okay, I'm going to like this feature for this one, but we know let's see. Okay, so if I take 7 divide 4 times 180, it's 315. Pi's canceling out, and we've got left 315 degrees. But what I do wrong? That should be negative. Okay, I didn't bring the negative over. Now it's there. So this wraps clockwise 315 degrees, or clockwise negative 7 pi over 4 radians. Okay, so for D, just a couple more here. 7 pi over 3 times 180 over pi is going to be equal to 7 times 180 divided by 3, 420 degrees. Okay, now here's going to be a kind of an awkward one with E. If we were talking about 3 radians, we don't have pi involved in this at all, so I just have to take that 3 times 180 over pi degrees. This time, since pi is not going to cancel out, this is probably a good situation to give the decimal form of degrees. So we'll take 3 times 180 divided by pi. Okay, I have to make the fraction, and then I'm going to take that by 3. So let's go out 3 places. We're going to get 171.887 degrees. Here's our next situation. We're going to take a look at how to calculate an area based on some radius and some inside angle that the arc here forms. So we're going to have a relationship where theta relates to some other theta 1 as the area, or the angle theta relates to the area of this red. So basically, the area of the blue is geometrically proportional to the area of the red based on the angle theta that is subtended by the arc that forms that little piece of pi. Okay, so we've got this relationship set up, and in this case, let's do this similar to how we did it with the arc length. And we're going to go ahead and say that theta 1 is equal to 2 pi. And we're talking radians, of course, no degree symbol there. So theta 1 is equal to 2 pi. That means it's the full circle. And we know a formula for the area of a circle. If you remember from a geometry class, or if you don't, here it is. The area of a circle is pi radius squared. Okay, so that allows us to plug that in. We know a theta 1. So let's put some arbitrary theta, and we locked theta 1 to be 2 pi. And we know that that relates to the area above, that should be A1. Okay, A1 is the area of a circle, theta 1. So theta 1 was 2 pi, and A1 is pi r squared. So all that's left in our setup here is the arbitrary something other than when the area is the full circle with 2 pi. So we're going to do the same thing and solve this for A. So if I multiply both sides by pi r squared, what do we got left here? Okay, so on this side, we're going to divide the pi out. So we're going to end up with r squared theta over 2 is equal to a. And we like to see that with the solved for variable on the left. So we're going to say a is equal to, and I'll just write the over 2 as 1/2 times r squared theta. Okay, and that's for an arbitrary area of a circle and then in the arc length that creates this area. All right, let's start with a situation where we're going to find the area. We want to remember that our area is equal to 1/2 r squared theta. Okay, we see this from the previous setup there. So let's find our parts here. We're going to find the area of the sector of a circle. Radius is 2 feet, and it's formed by an angle of 30 degrees. Okay, so we've got a situation here where we're in degrees, but we need to be in radians. All right, we didn't solve our formula for degrees, we solved it for radians. So let's take this 30 degrees. And remember, to get the radians from the degrees, we're going to take it times pi over 180. Okay, so that's going to be equal to pi over 6 radians. Now we can use our formula. So the area is going to be equal to 1/2 times the radius, which is 2 feet, squared, and then times the angle in radians. So pi over 6. Okay, so that's going to be 2 pi over 6, which of course we'll want to reduce to pi over 3. And that's pi over 3. The area, since the radius, circle radius is feet, this must also be feet. You want to see that in terms of decimal. Let's take okay, so that's somewhere around 1.05 square feet. Oops. Okay, this is the end of lesson 1.